Welcome back. In the previous video, we covered the categories of machine learning, which is supervised, unsupervised, as well as reinforcement learning. In this video, we are going to cover supervised learning. But specifically, before we get into that, I'd just like to cover and introduce you to Scikit Learn, a Python library. You can point your browser to this. I've already embedded the hyperlink for you. You just need to click. It will bring you to the Scikit Learn library homepage. So I've also embedded it here as well to allow you to actually see what it actually does offer. It offers classification, which is the supervised learning I mentioned in the last video. Another form of supervised learning is regression, unsupervised clustering, unsupervised as well, dimensionality reduction. There are many more Python libraries which cover machine learning algorithm. One of the best known is really Scikit Learn. The reason that it is so popular is because of its design. It is clean, it is uniform across all the different machine learning algorithm, and it is extremely streamlined, and it has a really good online documentation to walk you through from getting started all the way to become proficient at it. Now, what I really want to cover with you is really just start by covering some of the key data representation of Scikit Learn, how data is actually represented in Scikit Learn, how you can actually understand that clearly so that you can actually make full use of it and get up to speed and leverage on this really powerful machine learning algorithm Python library. So a couple of key points that I want to cover. First and foremost is that Scikit Learn make use of NumPy, and it is compatible with the pandas library as well. So when it actually represents data, it represents in the form of a table or two-dimensional grid of data. And what you have is that each row represents individual elements of the dataset or each sample, and the columns represent the actual quantities relating to each of these elements, now meaning the actual features itself in the so-called terminology of machine learning. Now, earlier in the same Iris project that we started in the first and second segment, we already imported the Iris data. So I'm going to go ahead and rerun all of these so that we load all the data into the Python library itself. So I mean the Jupyter notebook itself. So let's come down here. Okay, so it's just a continuation of what we did earlier. And let me just insert a cell here. You can just press A and they will insert a cell for you immediately. So let's see if we load the Iris data completely earlier. Okay, it did. Notice, I'll just refresh your memory a little bit. We stored the data of the Iris via the Seaborn library, load the data set and store it in the variable called Iris. And by using .hit, it shows you the first 5 rows of data. And what you have now is that you have the sepal length is one of the feature, the sepal width is another feature, and the petal length is another feature. So the data, as you can see here, is represented in 2D format. You have each row being each sample, and then you have the column being the actual feature itself. The features is in the form of a matrix. So you have 1, 2, 3, 4. It's a matrix in itself. Let me see if I can actually highlight this. So basically, it's in the form of a table. Okay, so you have this structure. So it's 2D format. If you go down this way in the row format, so you actually have the sample. Each row represent a single sample. Okay, so each row basically is a sample on its own. And this way is the column represent the actual features itself. Okay, so the features could be the length of the sepal, the width of the sepal, the petal length, or the petal width. The last column here is actually the so-called label or target array. Okay, so just highlighting the matrix part here really is that what we have at least in this structure is that you have 1, 2, 3, 4 and multiple rows of data. So essentially it looks like this. You have four columns and multiple rows all the way down depending on the sample size itself. So this is basically in the form of a matrix. And the actual last column in this data set here is actually the label or target array. Basically it's in this format. So the target array usually is represented as Y, so you have a vector or a column of data. So that's really these three key points here that I want to highlight. It's in the form of data. Okay, the data is in the form of a table. That's the first key point here. Second is that it is the features is in the form of a matrix, and the third is that the target array or the or Y or label is in this form of a vector. Okay, having understood that, okay, then we can actually move on to the next portion, which is the estimator structure of the API itself. Now remember that we are looking at the so-called machine learning algorithm here. At the end of the day, it's still trying to estimate the so-called algorithm or the function that represent the real-world data. And what we have here is that just to understand a little bit about the Scikit Learn API, how it is designed, this is the link itself to highlight how the API is actually designed. You can open up the PDF, and what I've done is that I've extracted some key points here, which is the general principles of how the actual API was designed. One of the key principles is consistency. Basically, it doesn't matter how many algorithms that you have, it will have consistent documentation, it will have a common interface as well. And the inspection part is that all the specified parameter values exposed as public attributes here. So you can actually see this. So basically what you have is not a black box, it's open and exposed for you to actually tweak, and you can actually see it as well. Non-proliferation of classes. Now, learning algorithms are the only objects to be represented using the custom classes. Datasets are represented as NumPy or SciPy, sparse matrices. As for the hyperparameter itself, the name and values are represented as standard Python string or numbers whenever possible. So the rest, I'm going to leave you to have a quick read to understand how it actually works. What I do want to actually progress to is actually the basic steps of the API itself. Just to walk through the basic steps of using the Scikit Learn API, the first part is that you need to choose a class of model that is appropriate for your data. So this is assuming that you've done your initial exploratory data analysis. So now you just want to choose a class of model to actually allow your machine learning algorithm to learn the data itself, the actual structure of the data itself. Then you choose the model hyperparameters, instantiating this class with the values that you want to actually specify. Then you arrange your data into features matrix and the target vector that we explained earlier. You have a matrix which is the so-called features itself, and also the actual ultimate target array itself. Then you fit your model by using the fit method and apply the model to your new data after you have trained your model. So let's walk through a simple example of simple linear regression. We already covered briefly the categories. So this is really under the supervised learning. So we are looking at simple linear regression here, and let's check out how it actually works in the actual Scikit Learn library and how you can actually make use of it. We already import matplotlib, so let's just generate some random numbers. We have the so-called x variable, which is our features matrix, so we're gonna generate 100 of them. Okay, so let's just use NumPy, the random generator, and random number, and we are going to generate 100 of them. I use 10 here to magnify, otherwise the your number is very small. The random number usually is between 0 and 1. Having generated our x, which is 10 times the numbers which is between 0 and 1, we want to now design our so-called target array. So this is basically what we're doing here, is that we design a model, or actually trying to generate some raw data to see if our machine learning will actually learn this structure or not. So let's just try 3 times x plus some random number. Okay, so we use NumPy, and again we generate another 100 and plot that out. Okay, so let's just use normally distributed. Okay, and let's just see what it looks like. So let me just plot this now. Scatter diagram of x and y, and let's see what it looks like. What you can see here is that x is between basically 1 and 10. Okay, because we basically 0 and 10 really, because the random number here generate numbers that's between 0 and 1. So 10 times 0 is 20, 10 times 1 is 10. So it's basically between this range. And y is 3 times x, okay, plus some noise. Okay, so let's just walk through the steps that we covered earlier. Okay, so the first step, as I mentioned before, is that we need to import from Scikit Learn the linear model. In this case, we're going to use the linear regression. Okay, so that's really the model that we want to use to model these raw data. The second one is that the second step of the 5 steps that we mentioned here is choosing a model hyperparameters. Now, once we have decided on the model, which is linear regression, there are still some options that is open to us. What are these? You might want to consider, hey, do you want to actually fit the intercept or the offset? Do you want to actually force it to go through the origin, meaning 0, 0? Do you want the model or the data here or the x-axis here to be normalized? Or do you want to use min-max or scale it? If you don't understand what I'm saying, we will cover that again. Do we want to actually pre-process our data, especially when we actually have multiple input variables? We need to actually consider that. So there are quite a few other things to consider, such as regularization and how many model components do we want to use. So we will cover that in future lectures. But right now, let's go through step 2, okay, and choose model parameters. So we're going to design a model, and we use the linear regression that we mentioned before, and we do want to actually fit the intercept itself. So okay, so if you print out the model, it will explain to you or print out to you, yes, you want to fit through the actual intercept itself, and normalize is actually false. Now the third step now is to actually arrange such that your feature matrix and also your target array is in the form of a matrix as well as in the form of a vector. Okay, so what we do here is that we set the so-called feature matrix, capital X is equal to small x, which we generated earlier. And then we do need to reshape this this way, because it must be in the form of a matrix. We only have a vector, so it won't work. It will be 0. So we need to reshape it. Now that it's in the proper form, which is in a matrix format, although it is in only one column, you still need to reshape. Otherwise, you're gonna get an error when you actually try to fit your model. So step 4. We've done step 1, which is actually choosing the class. Step 2, choosing your hyperparameter. Step 3 is actually arranging your data into a feature matrix and also target array format. Step 4 now is to fit your model to your data. So it's as simple as model.fit. Model is what we instantiated before. Fitting capital X and Y, our target feature. And that's it. That's fitted. Okay, so the next step then is to start actually predict the labels. But before we go into that, The class itself that we've instantiated and fit, it'll be interesting to see what the actual coefficient look like. The slope here is telling us is actually 2.95, which is pretty close to the 3 that we used earlier. And let's have a look at the actual intercept itself and see what it actually found, 0.25, which isn't too far from the 0. Well, because it's random, so it's roughly around there. And it's not too far from the so-called coefficient and the intercept that we specify. Now this, because it's a random number, normal number should be 0, well, with a min of 0, and 0.258 is pretty close to 0. It depends on what is the data that we generated. Now when you actually run this notebook, it's going to be slightly different because I did not set the seed or fix the seed, so it will likely to be a little bit different. And finally, our final step is to actually perform a prediction on what you call unknown data. So to do that, so we're going to do xfit. Okay, is we're just going to use the NumPy linear space, okay, from -1 to 11. Okay, so the next thing is that we do need to actually force this into the format of a matrix. So we just reshape this. And what we do next is to fit the model. Okay, it's model.predict, and using x fit. Okay, and finally let's plot the scatter plot, I should say. This is our original scatter, our original data set, which is xy. This is the original here, and let's plot the x fit and y fit. Y_fit, and there you go. What you can see here is that it pretty much recovered the so-called original features, which is the slope itself and also the intercept. And the straight line here is basically this. We basically have breakdown or segmented the x-axis into equal spacing, and we fit. We basically use that as our so-called independent variable, and we use our model to actually predict what the y value should be. What I'd like you to do now is that spend somewhere between 10 to 15 minutes, or as long as you like, and play around with this model that I've actually explained before and walked through with you. So I'd like you to pause the video and let you actually try out what happens if you vary this to 100 or 50 and vary this slope to -5, see how the data generates, and rerun these cells again and see what the slope looks like and how the actual cell perform itself. Did you manage that? I hope that went well, and basically that ends this lesson on using Scikit Learn. And now you can see how powerful it is because of the way it's designed, the simplicity, and also the consistency. And also you learn how to apply linear regression to raw data and even to the actual forecasting itself. So, so that's the end of this video. In the next video, we are going to move into applying this model into housing data and predict house price. I look forward to seeing you there.